Hello, my name is Deanie, and welcome to my brand new physics series. I'm not going to bore you with a long intro. Let's get straight into the physics. One thing I will say before we start is that I'm using the Fundamentals of Physics textbook by Halliday and Resnick, 10th edition, as the basis of my lessons. And I think it would be incredibly valuable for those watching to go and get that textbook somewhere and follow along and give it a read. It's a very high quality textbook, especially if you're a beginner into physics. Today we're going to start off extremely simple, extremely bare bones physics. We're going to talk about how we quote unquote measure stuff. Quote unquote measure stuff. How do we measure stuff? I apologize for my handwriting. Hopefully it'll get better as I get more used to this iPad setup I've got going on. But I think it's at least readable, which I think is important here. I'll tell you what, most physicists can't write for the life of them. So, how do we measure stuff? Well, first of all, what exactly is this stuff I'm talking about? Let's rename stuff into something else. This stuff is equal to physical quantities. Quantities. Let's highlight that because it's important. Basically, a physical quantity is a nice and fancy way for any values that physicists might want to know. Before I reveal some, try and think of something that would be important for a scientist or a physicist to be able to measure. I'm going to rapid fire some physical quantities, and I want you to see if you recognize any of these names, even if you couldn't think of anything beforehand. Mass. I would say you've probably heard of mass, you know? It's how much stuff is in you at a given time. What about time? I just mentioned it. You know, tick-tock on the clock. How long does stuff happen for? Temperature. You know? When is it appropriate to get your snowplow out, and when is it appropriate to get your beach on? You know? These are important quantities. What about one more? What about catalytic activity concentration? Huh? That one seems pretty important. Alright, I was kidding about that last one. I took that off of Wikipedia. I have no idea what that means. But I think the point stands that there's a lot of things that physicists would love to know, and these are categorized as physical quantities. Now, we just have to figure out how to measure them. So, measurements are a tricky thing. It's the basis of essentially all science. And measurements are taken in regards to something called a standard. So what is a standard? A standard, and let me move it down here so I have more room for my definition. A standard is essentially, hopefully I spelled that right, what scientists have decided is equal to 1 of whatever is being measured. For an example, I'd like to go back to one of those physical quantities I had listed earlier. Let's look at time. Now, even if you don't think you know it, I think you do know the standard for time. Take a guess, really quick. If you guessed 1 second, you would be exactly right. 1 second is considered the standard for the physical quantity of time. I'm kind of throwing out a lot of words, a lot of vocab here. Hopefully, it'll become a bit easier to talk about these things as if they're second nature once you get really into the physics and math of it all. A lot of this is going to be very new, and it will get more comfortable in your brain as you keep working on it. So if you're a little confused right now from even just that last sentence that I said, that's okay. it'll get easier. So when I said that the standard for time is 1 second, what is the unit? Take a guess. Now, if you said the unit is seconds, once again, you'd be absolutely correct. So I say the unit is seconds, and a lot of you probably knew what I meant when I said what is the unit, but honestly, what is a unit? What does it actually mean? The unit of a measurement is the name that we give to measurements of each quantity. So when I said that the standard for time is 1 second, the unit is seconds. And let's say if we're trying to find the length of something and we're measuring it in meters, the unit is meters. It's just the name that we give the measurement we're taking. Now, in that last example, I was talking about meters being a measure of length. But some of you might be going, well, hold on a minute. What about centimeters? What about feet and inches? Well, sorry for all the Americans, but meter is what was decided to be the standard unit for length. And I'll get into how that happened later in this video. Just to reiterate, length is the physical quantity that we're measuring. The standard for length is 1 meter, and the unit is meters. I should also mention that these units that we're using are not arbitrary, but decided in a way that can be replicated forever to confirm the exact standard for a quantity. Now, that didn't make a ton of sense, so let me give you an example. The second, as in 1 second, 1/60th of a minute, is now determined using something called a cesium clock, which will never ever deviate. Well, to be honest, it might deviate, but that's a problem for when Earth's rotation gets really out of whack, but we don't need to worry about that. These definitions are created to make sure that scientists around the world can agree and are practical for daily and experimental uses. So you say something took 10 seconds. That means the exact same amount of time all over the world because we have a standard way of defining the second that is the same for everybody. All right, so we have standards, we have units. How do we go about measuring things in the world? Especially when they're not so simple as time or length. Well, there's a very handy bit of terminology called base quantities. In the world, there are so many measurements that can be taken. But luckily, there is a way to break down the units of these complicated quantities into simpler ones. Let's take volume, for example. I'm sure you've seen the volume equation before. Let's say volume equals length times width times height. Let's say of a cube. This is the accurate volume equation. If we break this down a little, we can see that the units of this volume quantity will end up being some unit of length cubed. Now, how do I know that? Well, that's because length is obviously a unit of length. Width is also a unit of length, and height is the same, a unit of length. Let's say these are all measured in meters. That is the unit for both length, width, and height. So, what will the unit of volume be? Well, it'll be meters times meters times meters. So, the unit of volume will end up being meters cubed. And that's all fine and well, but I want you to notice something else. Like I said earlier, all three, length, width, and height, are measurements of length. And wouldn't you know it, length just so happens to be one of those very special base quantities. In fact, there are 7 base quantities, and nearly all measurements ever can be broken down to be some combination of these 7. Because of this amazing bit of simplification, scientists across the globe can now only have to worry about 7 standards rather than having a standard for every quantity possible. Could you imagine having to create physical quantities for volume, or for area, or for density, or for whatever other unit or measurement we have to take anywhere else in the world? That's a lot of standards to keep track of, and honestly, sounds exhausting, so that's why base quantities were defined. All other physical quantities can be defined in terms of the 7 base quantities. So let me define this really quick. All right, base quantities are the 7 quantities that all physical quantities can be broken up into. Beautiful. I'm going to do one more example just to really make it more clear. So I'm sure you've heard of the concept of speed, right? Speed is a measurement of how fast something is going. It can be defined as length over time. And, amazingly, length and time are 2 of the base quantities. But the unique way in which they are combined creates a new physical quantity to be measured, which is speed. Now, I want to go over the 7 base quantities. You will likely not be using a couple of these very much, but I think they're good to know just in case. I think the first 3 will be the most common, and then later on your physics journey, you'll begin using the rest of them. So let's go one by one. The first base quantity is length. Wonderful, wonderful length. So what is length? Length is the one-dimensional extent of an object. And the standard unit would be meter. And you'll often see length depicted as a big capital L. That's what physicists like to call the dimension. So if you see something with a big L, it is probably referring to length. Number 2 is mass. So this definition is probably not going to make a ton of sense until later on, but I'm going to say it how it really is. Mass is a measure of resistance to acceleration. Now, that might not make a lot of sense, but it will in the future. The standard unit is kilograms, not grams, kilograms, and the dimension is written as a capital M. Number 3 is time. Simple enough definition. It is the duration of an event. The standard unit is seconds, and you'll likely see the dimension referred to with a capital T. Number 4 is electric current. Now, electric current is the rate of flow of electrical charge per unit time. The standard unit is called the ampere, and it is commonly shown to be a capital I. Number 5 is temperature. Now, temperature is defined as the average kinetic energy, I'll write it as KE, per degree of freedom of a system. That definition is not going to make sense to you, and that's okay. most people think temperature of how hot or how cold something is, and to an extent, this definition means the same thing, but obviously you can read it and say, I don't think that's what I think about temperature, but you'll eventually learn what this means. The base unit for temperature is Kelvin, and you will likely see the dimension as this little degree symbol. Number 6 is a weird one. It is amount of substance. And this definition is going to be a long one. It's the quantity proportional to the number of particles in a sample with the Avogadro constant as the proportionality constant. Once again, that is going to mean nothing, but eventually you'll figure it out, especially if you're interested in chemistry, which I'll let you in on a secret. A lot of physicists hate chemistry, but they're both kind of the same thing. If you learn physics, you're going to learn chemistry, and if you learn chemistry, you're going to be learning physics. And both sides really hate that, but you and I right here, we love chemistry and we love physics. So the standard unit is going to be the mole, and the dimension is going to be a capital N. And the definition for amount of substance pushed me to the next page. Number 7 and final base quantity is luminous intensity. And it's defined as the wavelength weighted power of emitted light per unit solid angle. Once again, you will learn what all of this means in due time. The unit is candela, and you'll likely see it as a dimension of capital J. Awesome. Now we have a list of all 7 base quantities, and like I said, every physical quantity can be broken down into a combination of these 7. So that's extremely useful and an extremely powerful tool. It simplifies math in physics incalculably. Had a hard time saying that. All right, so now that everyone's favorite part of a lecture, which is the person talking just listing stuff, is over, we can move on to the next topic, which is a little bit of a history lesson. You might have been listening to me and been thinking to yourself, where did these 7 base quantities come from? Well, they came from a very, very important event in history called the 14th General Conference on Weights and Measures, circa 1971. So really, not that long ago. These units were made standard across the globe in 1971. So think about all of the struggles people before 1971 had to deal with when talking about science and science communication. Imagine trying to make conversion factors for all of your math just because you want someone in a different country to understand your work. Can you imagine how much time that would take? How frustrating it would be to basically learn a new language even though you're all doing the same math? That's why it's so incredible that these units exist. They're extremely useful, and Without them, we would be spending a lot more time trying to figure out what other people are saying rather than understanding the work that they're doing. So, at this general conference on weights and measures, something called the International System of Units were invented. And this system is very important. I'm going to be referring to them as SI units moving forward. SI units. And that's how you'll be reading them pretty much everywhere else for the rest of your life. Why is it SI? I think it's French. I'm not sure. You may also know it by a much more common name, the metric system. Americans interested in science, I'm sorry, but you're just going to have to deal with the metric system. So, like I said, nearly every physical quantity can be measured in terms of these base quantities, and we call those SI-derived units. So, if there are units, physical quantities that we're measuring, that are made of the 7 base quantities in some fancy combination, they are called SI-derived units. And they're derived from the base quantities. Hopefully that name makes a little bit of sense. Let's look at an example. The unit of newtons. You might be saying, hey, that's not a unit, that's a guy, and I didn't know there were multiple of them. Well, no, it is a unit. It was named after him. The Newton is the unit of force. You're going to learn all about force in the coming lectures. So this is a derived unit. Which of the 7 base quantities is it derived from? It's derived from mass, time, and length. 1 Newton is equal to 1 kilogram, 1 meter per 1 seconds squared. Kilogram is the standard unit for mass, meter is the standard unit for length, and seconds is the standard unit for time, and in this scenario, we're squaring it. That still means it's based off of time. So you see that units can have their own name, like Newton, but still be fundamentally made up of the base quantities. It's just a name that makes it easier to work with. It would get really tiresome if you had to say 1 kilogram meter squared per seconds cubed every time you wanted to talk about the wattage of a light bulb. If you're curious about what I just said, 1 watt is 1 kilogram meter squared per seconds cubed, by the way. Now, there is another way of naming certain units if there are numbers that are extremely small or extremely large in comparison to the standard. And this is something we like to call scientific notation. Now, doesn't that just make you sound super fancy? I'm using scientific notation. Well, it's actually not that complicated. What scientific notation does is it uses powers of 10 to simplify these numbers into something easily readable. So let's say we have some measurement of 2 million miles. That's a lot of miles. So I don't want to keep writing down all these zeros. We can write it as 2 times 10 to the 6th miles. And just in case you're a little confused about what I just wrote, it is 2 multiplied by the number 10 to the 6th power. If you don't know what that means, the 6 is called an exponent. It means essentially multiplying a number by itself a set amount of times. So this would be 10 times 10 times 10 times 10 times 10 times 10. That's 10 to the 6th. If that's something completely new to you, I recommend looking up exponents and seeing how they work. You're going to be using them a lot in physics. Now, notice something. I wrote 2 times 10 to the 6th. I only have one number in the ones place. That is a rule of scientific notation. The valued number must have only one digit to the left of the decimal point. If you're saying, hey, where's the decimal point here? This is equal to 2.0 times 10 to the 6 miles. To the left of the decimal point, there's only a 2, and that's how scientific notation works. Only one digit left of the decimal point. Really, really hammer that in. Let me write that down as well. So I said there can only be one digit to the left of the decimal point, but that does not mean there can't be any digits to the right of the decimal point. I'll work another example and show you what I mean. Let's say we have a measurement that's 53,280,000 seconds. That's an ugly number. I don't want to work with that number. So we can write this in scientific notation as 5 decimal point, because remember, we can only have one digit left of the decimal point, 328 times 10 to the 7th seconds. There is only one number to the left of the decimal point, but there can be numbers to the right of the decimal point, as you can see with 328 here at the end. Now, I've used some pretty big numbers, but this also works for small numbers. Let's say we have a measurement of 0.000000356 kilograms. This can be written as 3 decimal point, once again, one digit left of the decimal point, 56 times 10 to the 7th times 10 to the negative 7th. Excuse me. Once again, if that exponent is not something that you really understand, I recommend looking into it. But just to be simple, instead of pushing the decimal point to the right, like it was going on up here with the positive exponents that I just circled, now with a negative exponent, it's pushing the decimal to the left. So let's say the decimal starts here in scientific notation. A negative exponent is going to push it to the left, and a positive exponent is going to push it to the right. Now, chances are you have a fancy calculator like a TI-84 or whatever, or you have a computer, and you've probably seen the exponent part represented a little differently. Let's take our earlier examples and see how they would look like on a computer. 2 times 10 to the 6th would look like 2e6. 5.328 would look like 5.328, and then it would be e7. And then the last example would be 3.56e negative 7. Hopefully you can see the trend here, but if you don't, the e, capital E, is equal to 10 to some exponent of the number after the e. The e just means exponent of 10. So 2 times 10 to the 6th is 2e6, if that makes the comparison a little easier to figure out. Now there is one more way of naming different units, and this one is not necessarily naming the units, but giving it a bit of a description. You can use what we call prefixes. You may have learned that prefixes are little chunks of a word that gets added at the beginning to give it a bit of a modifier, and this works nice in science. It's to deal with large or small numbers, similar to scientific notation, but in a little different way. You've probably heard of the unit centimeters, right? Well, what about millimeters? Sound familiar? Well, centi and milli are both prefixes for the unit of meters. Meters I was talking about all day today. Each prefix, very similar to scientific notation, represents a factor multiplied by the original unit. I'm going to list some common ones that you'll hear. For centi, it's 10 to the negative 2. For milli, it's 10 to the negative 3. For micro, it's 10 to the negative 6th. And they can go in the opposite direction. You can make it a bigger number, like for kilo, which is 10 to the 3rd. And giga, which is 10 to the 9th. You know? And I'm sure you've heard these before. Like, what about a gigabyte? Like how much storage is on your phone? That giga is 10 to the 9th factor applied to the unit of a byte. Or a kilogram. That's a 10 to the 3rd factor add to the unit of a gram. So I'll do one quick example. Let's say I have 1,000 grams. And I want to write this in kilograms. Well, the factor is 10 to the 3rd for grams, which means the amount of kilograms with a factor of 10 to the 3rd added to it is equal to 1,000. So what we actually have to do is go a little bit backwards by saying 1,000 grams is equal to 10 to the 3rd times mystery number of kilograms. And if we do the math here, we'll find out that it's actually 1 kilogram. We've gone through quite a lot today, including a lot of units. So how do we change the units of a value to something else? Well, we can use what's called a conversion factor. Conversion factors are not really that complicated. It's a fancy name for a ratio of units that are equivalent. For example, let's look at 1 foot. The Americans have had to deal with the metric system for this entire video. Let's throw them a bone, right? 1 foot is 12 inches, correct? I think so. And what I just wrote down here is a conversion factor. It's a ratio of units. 1 to 12. That's the ratio for feet to inches. We can use it to convert one unit into a different one with simple division. Let's do an example using the conversion factor I just wrote. 36 inches is equal to how many feet? You could probably do this in your head, but I want to go through the long way just to show how conversion factors work, because you'll be using these a lot and it's usually not so simple as 36 divided by 3. So, 36 inches. Let's apply our conversion factor. We'll multiply our conversion factor, and you'll notice that the unit of inches is in the numerator with here and in the denominator here. What ends up happening in conversion, and you can try this with any conversion factor and you can prove this to yourself, that the units actually cancel. If it's in the numerator and the denominator, these units will cancel, leaving us with just the unit of feet, which is exactly what we're looking for. And that leads us into 36 over 12 feet, aka 3 feet. And these conversion factors can go the other way as well. Let's say I had 3 feet and I wanted to know how much that was in inches. We can use the same factor except the reciprocal of it. So we'll put inches in the numerator. 12 inches is equal to 1 foot. Foot in the denominator. I wrote foot and feet, they're the same thing. We cancel out the common units in the numerator and the denominator, leaving us with 3 times 12 inches, aka 36 inches. We use the same conversion factor, just the reciprocal of it, and that shows that these conversion factors are indeed reversible. Excellent. This is all for my lesson on measurements and units. I hope this was helpful, and I'll see you in the next lesson. Like and subscribe if you enjoyed, and happy learning.